So we talked about family P, NP, and a part of NP which is called NP complete. We talk about decision problems and Turing machines. Why we need two Turing machines at all. Class P, class NP. Class P is the good class. NP is the bad class, like the difficult class. So you don't like NP. And NP is, so class NP, not the word NP. NP can be like non-polynomial, but the class NP, it doesn't mean non-polynomial, means non-deterministic polynomial. And we talk about polynomial time reduction. Polynomial time reduction, it means that reduction in polynomial time. Reduction means converting one problem to another problem, which is the second problem is more difficult than the first problem. We will talk about it. So reduction doesn't mean reduction in complexity, it's reduction in the difficulty for human to understand the problem. So we will talk about NP hardness. NP hardness and NP completeness. Hardness, I said, means difficulty. Completeness, we will see later. So NP hardness being as difficult as NP. NP completeness, it is another level of it. We will talk about it. Cook and Levin were two scientists which proved the first ever NP complete problem. So they showed that the satisfiability of Boolean formulas is NP complete. So they proved that. This was the first time that something was proven to be NP complete. So we'll talk about examples, and we will talk about the fact that we still don't know if P and NP are equal, and what will happen if we find out that they are equal. We said that P is inside NP. Here we should not have an overlap, and NP complete is a part of NP. Whatever is in P is in NP, but we don't know if whatever is in NP is also in P. Okay. Again, I repeat the example for non-determinism. So when you say that NP is non-deterministic polynomial, in short, it means that you need parallel computers. You need many processors to solve this problem in polynomial time. It means that you say, if I had 2 million processors, I would solve this problem in 2 million different threads, ways, that each way, I mean, a way doesn't mean style, it means the root, the thread, would need a polynomial time. Yeah. So I gave the example that the deterministic system is like an airport or air travel. You have two airports, and you have a ticket. The ticket is the input to the source airport. So you give the input, you show your ticket, and you can go to just one airport on the planet, just one airport. So it is very deterministic. With this input to this airport, your state can change to just one specific airport on the earth. You cannot go anywhere else. It is clear, it is deterministic. Non-deterministic is when you have a metro ticket and you can go everywhere. So if someone asks you with this metro ticket, how can you the fastest reach home if you live in the two-dimensional way and you don't see the map from the top? You will say that if I could, so let's say in the airport, there are 5 metro lines. You say, if I could copy myself to each of these lines, and on each next station that there are other lines, I could also copy myself there. Then at the end, if I had like a 200 copies of myself, then in a polynomial time, it means that, I don't know, after, if the whole city has 500 stations, you would say that after like 5, 20, 30 stations, I would reach home. Yeah, I would reach home for sure. For sure, at the number of stations that I would traverse would not be more than all stations of the city. And it is clear, you just go, it's like you just go once. Your copies start from the source to the destination. Each of them reaches the destination. All other copies vanish away, and your most successful copy will be at home. This is non-determinism. You need parallel computers. You need to copy the problem many, many times. At each time that you have at least 2 states in front of you, because you have a metro ticket, and with that metro ticket, you can go everywhere. On each station where there are more than one line, you can go to at least 2 different places. So it is non-deterministic. Each of those thread has a polynomial time. So none of them is 2 to the power of the number of stations in the city. No. Each of them is small. But if you consider all of them together are, so you have like 200 copies of yourself. If you sum all the ways they have gone, it is much bigger, or all the stations that they have seen, it is much bigger than the number of the stations of the whole city. Each station has been seen many times, but each copy of you has seen its station just one time. Or let's, yeah, depending on the problem, it can be, it has seen just 2 times. I don't know, n powered by 2 times, but it is never 2 powered by n. It is never n factorial. Yeah, this is non-determinism. When you talk about NP, class NP needs supercomputers with many, many CPUs. And even with them, because many, many CPU doesn't mean unlimited. So if you want to crack an encrypted message, which is well encrypted, theoretically you can do it, but practically you need unlimited, a lot of time and a lot of processors. So NP is that non-deterministic polynomial. We don't like it. We don't, for today, computers cannot solve these problems easily. P, we like, no matter how difficult they are, with one processor, you can solve them. And in reasonable time. Problem is big, we work more, but we don't need to copy ourselves. So this
Professor,
is, yes?
You have mentioned in the non-deterministic example that we have two states in front of us. What are you referring to?
Um, so this is a deterministic system. You go from here. You have a ticket from here to I don't know, to Paris, and from there, if you have a ticket to Berlin, you go to Berlin. If you have a ticket, I don't know, to New York, you go to New York. This is deterministic. Here, this is non-deterministic. You arrived in Paris, but you have a metro ticket. You can go here or you can go here. This is non-deterministic. It means that with the same input, you can go. So actually, this can be considered as an input to this, or this and B together can be considered as an input to the system. So there is a system of airports. You give the name of the airport and the ticket that you have. You can use this ticket. The system can tell you where to go. But this is the airport system. This is the metro system. In metro system, you have the same ticket, but the ticket can bring you here or here. You can go anywhere. So if I say I arrived to Paris and with my metro ticket, I continued. So where did you go? Where did you go? You could go everywhere. So this is non-deterministic. I cannot determine where did you went. But if you say I went to Paris, I had uh, a plane ticket to Berlin. I know that you have one here. This is
So
deterministic.
you wouldn't know the outcome until there's like a result or something that proves I went to somewhere.
Yes. Here, before, without you tell me where you arrived, even if you tell me the destination, I don't know how you have reached it. Determinism, non-determinism means uncertainty. So here, with the same action, you can end up in different results. This is a non-deterministic system. When you say also you are in a non-deterministic finite automata. The characteristic was that you could like this. You could even go back to yourself and go back to the same state. So this is non-determinism. Means that in the same state, with the same action, you can end up in different places.
Okay, I got it.
Yes, you can loop forever here, you can go here, you can go here, and you can continue. This is, so if in such a system, you want to know the solution, so the solution may be a city here, the shortest way. Here, this guy should copy himself or itself to all of these, and each copy continues. Perhaps here also we have something like this. If we have like something like this, even here, it should copy itself to here and here. So in order to find out the solution. When we say it should copy itself, we are talking about like about non-determinism. And yeah, of course you can go here, see till the end. You can write it somewhere like DFS, BFS. You traverse it to some point. You write on the stack. So, hello, I have been here. I came from here. I came from this state to this state, and now I'm going to the left. You write it here, and you continue your way to the destination. Then you come back. You from the on the top of the stack. You read, oh, okay. This has been my past here, and then you put this in your bag, and you come back when you are here. You tell your friends. How was the way? Yes, and then you go again. Say this time I will go from here to the right, and then you here also you put here here and here you write a note. I was on I was here, and now I'm going to the right. When you come back, you read your memory from the top of the stack, and then you continue your way. And then when you are here, you tell your friends, okay, this time I went this way, and now the way was longer or shorter. So this would be, and this is difficult, you know. You either have to traverse all of them, or you should use your fantasy that you are copying yourself. Uh, yeah, none of them is really a straightforward solution. Yeah, by the computers that we have today. Yes, so non-deterministic polynomial. Um, and it is very important, very important. Also, when you are talking in your projects, you are explaining things. Verifiability. This is the key to NP. Not that if you have a problem which doesn't have a polynomial solution, it is NP. No, this is this can be misleading. The problem should be, I mean, a solution to the problem should be easily verifiable, which means that it should be verifiable. You cannot solve this problem. You cannot solve this problem. But if I tell you a way, you can easily verify if this is a good way or not. I told you to go to Y. Then you show me your way. I say at the end there is a Y. Accepted that this is one way of. So this is one. We say a certificate. This is a certificate. You should have a short certificate for this class. We will go to this a little bit later. Okay, let's see. Please listen. What I'm telling you is very important, and it connects different things that you know, but you don't know why you have learned them. It connects different things to each other. This is very important. So mathematicians, like they know these things. When we study as computer scientists, we study math. We don't get to all of those details, and we may not be able to connect the things to each other. So, but listen to this. This is an important. So there are good students that know two branches of science, but they don't know that why they have learned them. So this is the reason I'm telling you about why we need Turing machines. Yeah. So decision problems. A problem whose answer is yes or no. So you have, let's say you are in binary system. You have a computer which receives zeros and ones, a string of zeros and ones, and says yes or no. What does that mean? This is a decision problem. So you have given a problem, the answer to which is yes or no. Let us go back to here. I ask you, is this number divisible by 2? You just say yes. I say, oh, how smart. I say, okay, divide it. Then you say, hey, give me a day, I will divide this by 2. So you just looked at the 2 at the end, and you told me, yes, it is divisible. So the fact that you could say that there is a problem, there is a solution, is a yes, no, is a decision problem. So actually, what went to your head was this and this and this. You have this. Can I divide it with 2 or not? Yeah, this is the problem. This is what went to your head. This is the binary string that goes to a Turing machine, to a decision maker. So we have converted the problem of division by 2. Instead of asking you what is the result of dividing this number by 2, I just asked you, is this string divisible by 2 or not? The whole string that I have here, the whole string that I have here is the input to the function. So this the combination of zeros and ones that you see here is this. This is the whole problem. And you say yes or no. I ask you, is this one, can you divide this by 9? Say yes. If I sum these with each other, it will be 18. 18 is divisible by 9, then I can divide it by 9. Yeah. So this is the string which goes to your head. The result is yes or no. And we have a purpose for doing this. Yeah. Listen, this is not, no one teaches like this because people who teach these are mathematicians, and they think they are talking to mathematicians. Now, an engineer is talking to engineers. So this is the connecting point. Why do we need Turing machines? You can read the whole book about Turing machines, understand them, but then you ask yourself, this is just accepting and rejecting. Why do I need that? So now you have an idea what does mean converting a problem to a yes-no problem. Yeah. Why? Say, if we can't even decide, is there a solution of the cost, whatever, to the problem, we certainly cannot find the solution. So if you even cannot tell me if you can divide that by 2 or not, probably you don't know you don't know how to divide. Yeah. This was like an exaggeration, but we don't talk about this. We say, if we have a different, okay, this is the official or formal definition. Optimization and search problems means these difficult problems that all of them are NP problems. are at least as hard as their decision versions. Let's go back. Finding the result of this division is at least as difficult as saying that this division is possible or not. It is at least as difficult as saying that, that if the division is possible or not. Saying, just looking at this and saying, can I divide this by this, is at least, sorry, dividing it, doing the proper division is more difficult. It's more difficult. It's at least as difficult as saying that if it is divisible or not. And if you are a system uh, which even cannot, you're like, yeah, you are a system that even cannot say if a solution exists or not, probably you cannot solve it. Yeah. And this gives us a baseline for solution. I gave also this example. I'm at the university. I know that Dubai Mall is, let's say, 1 kilometer from here. I know that a human walks the distance of 1 kilometer in 13 minutes. Yes, I know that a human walks this distance in 30 minutes, 13 minutes. Then I am capable of saying that. It means that I know the direction, I know the approximate distance. Going to from here to Dubai Mall, it takes at least this amount of time, at least 13 minutes. If I cannot tell you this, it means that I don't know where Burj Khalifa is or where Dubai Mall is. Yeah. The fact that I can tell you the air distance and I have an approximation of the best solution, that is we say the bottom line, the lower bound. The lower bound maybe is not achievable at all. Is not achievable at all. So it's impossible to walk from here to the Dubai Mall in a direct way. But that approximation, um, saying that approximation is easier than really finding a way from to here to there, finding a proper way from here to there. And I know that I have a baseline for saying how good my way, how to say, the routes that I find are. We have a concept like we say, this system is a two approximation. What does mean two approximation? It says that it is never more than 2 times worse than the baseline. The baseline is maybe definitely impossible, but now we have a number to talk about. Yeah, we have a number to talk about. So that is why we need machines, systems that could tell us if a solution matches a problem or not. If a solution matches the problem or not. This yes, no. So I say, can I go to Dubai Mall in 5 minutes? No, you cannot go. Is it no, you cannot go. This is impossible. Can I go there in, I don't know, 2 hours? Yes. we have a two approximation of that. You can also go into 26 minutes. So if I give you a number and a problem, a solution and a problem, and you can accept or reject, this is a good baseline to study that problem. This is a good baseline to find the family of that problem. Yeah, so there are examples of such problems. Path. So if the original problem has been find a way from source to target. Find a way from source to target. This has been the original problem. But now if you change it to decision problem that can be tested with the Turing machine, it sounds like this. Given graph G, vertices source and target, and an integer k, does graph G have a path from source to target of a length which is shorter than k? Canadian University, Dubai Mall, 15 minutes. Is there a way from, in this graph of the city, from CUD to Dubai Mall, which is shorter than 15 minutes, shorter than 1 hour, shorter than 13 minutes, shorter than 13 minutes? No, rejected. No, there is no way like that. So we will learn in the if in summer you or in the next semester you join this course of computability and complexity, we can go we will go deeper, or I mean, not this course, you can also take a book and read deeper how, by looking at the characteristics of the decision version of a problem, you can guess the complexity family of the problem. That's a beautiful science. Now that programming is as easy as writing a prompt, solving such problems makes you a programmer to decide where to go. Yeah. Primes. Finding out if a number is, generating a prime number is difficult, but saying if a number is a prime or not is a bit easier. So it is a yes-no problem. By studying the nature of this yes-no question of if a number is prime or not, you can understand the complexity of even production of prime numbers. Given a Boolean formula f, this is SAT. This is like without this problem, the complexity course would not exist. At least not for computer scientists. This is let's say the mother of problems in a good way. So given a Boolean formula, Boolean formula is like A and B or C and D and or and it's such formulas, a Boolean formula that can be true or false. Is there an assignment of variables making phi true? We should have these shapes here. Anyway, I wanted to find an end here. let's say I say A and B, let's see, for example, V is an OR. So this is a Boolean formula. Right? This is Boolean formula. Or C. An assignment of this is, for example, if A is true, B is false, C is true. This is an assignment. True, false, true, false. So these are assignments. Instead of asking you, find an assignment which makes this true, which is a difficult task. A yes-no version of this is that I give you an assignment. I say, if A is true and B is false and C is true, is this true? Is it satisfied or not? Yeah. Is it satisfied or not? So this is the yes-no problem based on true or false. This is the problem set. We don't ask, how is this formula satisfied or satisfied? We say, this is a combination that I have. Does it satisfy the problem or not? The problem click. The problem click is the problem of finding if in a graph there is a cluster of nodes which are fully connected to each other. There's a cluster of nodes which is fully connected to each other with the size k. So I say a 5-click is a cluster of nodes with the number 5. So I'm using 5 nodes inside the graph, which are fully connected to each other. All of them are connected to each other. I don't ask you, please find a 4-click in the graph for me. I don't ask you, please find a 6-click in the graph. No, I ask you, I give you a graph and a number. You just tell me if there is a k-click or a bigger click inside it. So I just give you the graph, an integer k, and you tell me if there is a click inside it or not. So I didn't ask you to find that click for me. I ask you if it exists. So you are simply, not simplifying, you are changing the problem from finding to verifying. Finding to verifying. These are verification. I give you a solution, you verify it, you don't find it. Here, finding in all of these, finding is non-polynomial. Finding is non-polynomial. The fact that I can verify the solution, it makes it the family NP. So the NP doesn't mean non-polynomial. The fact that these are not polynomial and we have a verification mechanism based on a certificate, that is making the problem being an NP problem. So verification is important. Each of these can be, if you have a solution, uh, one can verify that solution in polynomial time. You have a certificate for that. Certificate is the checklist in the hand of an inspector. It is a predefined checklist. The inspector, so I said this example, you are computer engineers on the weekends. So I had friends like who did this. They had a part-time inspecting job. They went to customs or somewhere that something was installed when I was in Germany. So these friends did not have any idea about mechanics and anything. They had a checklist, a certificate that they would give to the product if it was completely verified by that checklist. So that is a certificate. And this certificate, we say it should be a short certificate. If the certificate, so if so this guy has a part-time job on the weekends, and we tell him, so you need a 4-year training for that. So what kind of that? I'm an inspector, not an engineer. Yeah, I'm a computer engineer. I'm not a mechanical engineer. That is not a certificate. If you need to read 5 books and study for 2 years to get that, to learn that, it's not a certificate, it's the whole knowledge. Then we say you can find the solution. You can find the solution. But here it's like we have built the system, you just verify it. We didn't ask you to build a car. We show a car to you, you just say it moves or not. If it moves, everything. So I even don't know how a car engine looks like, but if I can drive with it, I say the engine is healthy. This is a short certificate, a yes-no problem, which tells a lot about the complexity, but the person who is verifying does not need to have that knowledge. So these problems, which are finding the solutions for them is very difficult, but they have short certificates which can be verified. These are NP problems. Without having that verification mechanism with a short certificate, no problem can be claimed to be in NP. Even simple problems, if you have a simple problem that you can produce or find a solution to it in polynomial time, and you can also find a verification system for that. That also is in NP. Yeah, it is in P and NP. Yeah, all problems are in all P problems are in NP. So this is an example for, let's say, click. We have a graph. So the graph, what is a graph? Graph is also a string. Yeah, graph is a string. You can build it. Even what you see here is a string of zeros and ones that are transformed to this shape that we can see in this visual system. So our graph is a string. Integer also is a string. Yeah? So these are a bunch of zeros and ones. They go to our algorithm, whatever it is inside the machine, it says yes or no. Graph number. Does this graph have a k-click or bigger click? Yes or no. This is the mechanism. And the system, the machine, the function inside the Turing machine could do that in a polynomial time. In a polynomial time. So n is not in power. K is in power. So in polynomial time, we could say yes or no to a solution or a characteristic of a solution. Does it exist or not? Could we build such a Turing machine? Yes. Then the problem is in NP. The
Actually,
class, yes.
why can't, for example, if I'm solving a problem, for each step I just assume something, and then if it's wrong, I'll go back.
So that makes it an NP problem, no?
Yeah, but isn't this like an efficient way to get a solution?
If it is a search problem, it is a possible, it's not an efficient way, it is a possible solution. You are in a city, you want to go from somewhere to somewhere. It is possible to go to every junction and continue. And if you don't reach the destination, you come back and then continue. 2 years later, you have found the cafe that you were looking for. It works, but it is better if you look at the map of the city from the top, you are in a higher dimension. Yes, the
Mm,
city, the surface of the city is a two-dimensional world. In the two-dimensional world, you don't have a polynomial solution for that. Then you look from the top, you are in the third dimension, you can solve this non-deterministically. It means that from the top, you see all the ways at the same time, and you choose the best one. If the city is small, yeah, this is the way that you solve the problem. You have a heuristic. Heuristic means that you have a logical approximation, a logical way to find an approximate solution. From a higher dimension, you look at all solutions at the same time. This is a better way than traversing all possible routes.
okay.
Yeah. So what is class P? We talked about it. So we are not talking about a polynomial, a problem which has a polynomial solution. This is a family of problems. And the criterion here is the behavior of a Turing machine. Turing machine says yes, no, yeah. P is a class of decision problems. Decision problems. Yes, no problems. Solvable by a deterministic Turing machine, by airports system, yeah, is a decision problem solvable by a deterministic Turing machine in a polynomial time for some complexity and based on the length of the input. So it is O n powered by k. N is the length of the problem. How big is your city? How big is your problem? I mean, the size of the problem. And k is constant. So no matter how big the city is, I will give you the solution, for example, in the number of junctions powered by 3. So, or one can say polynomial problems are problems which tractable algorithms. It means that they are, so when I told you you are in metro and you copy yourself, of course, this is something strange to say, yeah? But in computers, we do that. We copy the problem. We can copy the problem and they go in parallel and come back, yeah? We can do that. But what is straightforward is not copying yourself. So with one CPU, within 2 hours, you get the result. That's something good. You have determinism. These are the P means tractable, efficient, good problems. So when we talk about the language, a language is a set of strings which have a meaning inside a system. They have a common characteristic. So, and because we are in the world of computers, 0 and 1s. You get this English sentence. This is a bunch of zeros and ones which have a meaning in English language. So a language is a subset of all strings. This is all strings possible, which have a meaning. So if this language has the following characteristics, there is a Turing machine M which accepts an input X if X belongs to L, and the acceptance process is done in a polynomial time depending on the length of that input. I read it again. A language L, so the class P, is the set of all languages, let's say in a binary. This is not important. Yeah? You can have any alphabet here. Class P is a set of all languages so that there exists a machine M and a polynomial formula such that for every input X, the machine M would accept X in polynomial number of steps as a function of the length of the input. And the fact that M has accepted X means that X is in L, and if X is in L, then M accepts X. So the magic word here is polynomial. In short, there is a Turing machine which in polynomial time can say if an input belongs to a language or not. So for example, we know that 3 factorial is 6. Yeah. I build a Turing machine. I give 3 factorial 6. I'm not calculating 3 factorial. I'm just giving this to the machine. If the machine can say yes in polynomial time, depending on the length of my input. The length of input is this. So if I open this and write it in binary, and I see that, hey, I see that the system can tell me yes or no in 2 times the length of the input, or n power by 2 of the, like the length of the input powered by 2. If in that time the machine can say yes or no, then this yes-no problem is in class P. I found a machine PM, Turing machine M, that in polynomial time can say yes or no, can accept or reject in polynomial time. Then the conclusion is that this language, the language in which each 2 numbers have the relation that the second one is the factorial of the first one with the factorial in the middle, or it can be also something like this. This language of factorial is in P. This is a language. This is a set of strings. Yeah, this is a set of strings. These are the examples of P problems. N is the problems in P. That is better to say it like that. N is the size of the input. If we have a graph, V is the number of vertices, and E is the number of edges of that graph. You see, so sorting is O n log n. In polynomial time, polynomial, you'd never see here that you never see that n is in power. Power is something else. It's power of 1 divided by 2, power of 3. There is no power here. There's no power here. If there is a power, n is not in power. As we talked about this, we have something here. Yeah, so these are examples of problems which we know that are in P. Class NP. Okay, class NP. Non-deterministic polynomial time. You should have a verifier, or let's say you should have a certificate and verified come together. Yes? So verifier definition. Yes.
Can you repeat what was a certificate?
Certificate is a checklist of an inspector. Certificate. So this is a little bit misleading. Certificate is usually the paper that you get after you are checked. But here we say that a certificate is the checklist itself. So for example, certificate of, I told you, you can give a certificate to this and says you can divide it by 2. And you don't need to divide it. You just look at the 8. The certificate is the last number divisible by 2 or not? Yes. Then you can divide it by 2. This is the certificate. You can verify this, the fact that the problem can be solved or the solution is correct. So I can put a 2 beside it. And this can be the input to the Turing machine. This can be the input to the Turing machine. It looks at this, and this, and says yes or no. It is yes or no. It has a certificate. It just looks at the end. This is a certificate. Yeah.
So is it like an assumption
No.
that proves if something is solvable?
It is not assumption. Assumption is what you have decided. So I assume that all of you know that 3 factorial is 6. This is not an assumption. This is a potential true correct solution. You can also call it an assumption, but I have never had someone in this context to use the word assumption. This is not an assumption. This is a potential solution, or this is a potential candidate for our language, the language of numbers which can be divided by 2. So this is a string that belongs to our language. So another string could be this is the problem and solution. These are both two members of our language. And the system receives this and says if this is in the language or not. The certificate, if it receives, if it can be checked or it passes the certification, let's say, it passes the fast certification, then it is accepted. If not, it is rejected. Here, also we say the verification against the certificate. Verification definition, verifier definition. Language L is in NP if and only if there exists a polynomial time verifier and a polynomial P. Polynomial P means like n square n to n log n something like that. Yes. So L is a member of NP, the language. You see, this is a language. The language L is in NP if and only if there exists a polynomial time verifier. What was our polynomial time verifier? Just the inspection method or the system that looks just at the end of the first one and sees if that is divisible by the last number. Yeah? So there exists a polynomial time verifier and a polynomial P such that if X is a member of L, like for example, this is a member of L, but this is not, because we cannot divide this by 2. Yeah, this is not. So if X is a member of L, then there exists a certificate C, which is a short certificate, and the verifier can use that certificate and say yes. So my certificate was checking the last digit, and that check the last digit, going through it takes a polynomial time, and this polynomial time is less than a polynomial function over the length of our input. Look, the length of our input here, I don't know, is 20, here is perhaps 10, or here is 30, here is 10, I don't know. This is the length of our input. Checking the last digit takes less steps than the number of the steps that we should take to solve the problem, or the
So,
number,
Professor,
yeah, of
it's
digits
like
of
a
this
small
problem.
fact.
Yes, small, it should be small, check.
It's like a small fact that proves if the problem is basically valid.
If the solution and problem match each other, if the problem is valid, yes.
Okay.
You say if the problem belongs to our language. Yeah. And you see, although this is not in the language, but we can, what we say is valid. Here, we could reject it in polynomial time. We just looked at this and said yes or no. We said no. Here we said yes. Yes. As Sarah said, is a short proof that X is a yes instance. Certificate is a short proof. It should be short. It should be, and what does mean short? It means that it has less steps the being short can be shown in different ways. So this is one way to show it. A polynomial function of the length of the input is bigger than the length of your certificate. And the length of certificate actually is the number of steps that the certificate takes to check is the problem. So class NP, always forget to put a dot here. Finding a solution could be exponential, but verifying it is always polynomial. So finding a solution could be exponential. It means non-polynomial. For example, in SAT, the certificate is it's satisfying assignment, like true, false, true. The verifier, you just put the values and into your formula and see if it's correct or not. So if I have A and B or C and D, and if you tell me false, true, true, how long does it take for me to check if it is true or not? 3 steps. I just put this here, put this here, put this here, and then it's like, let's say 6 steps. And then I find a reason to say that it is wrong. If I cannot find that reason, it will be true. Then this is verifiable in polynomial time. It's O n, and n is the length of my formula. This is the formula. See, this is the formula. Hamiltonian path. A sequence of n vertices. So this is the input. The verifier, you check if they make a sequence from the beginning to the end, and they don't they are no vertex is repeated. So do you remember here had here we had this machine. Here we have this mechanism, which is comparing 2 different solutions. So if you find a click, it is in NP, is an exponential time. You have to search the whole all subsets. You should search check all subsets and see if they are a click or not. Okay? You should check all of them. In verification, you have the vertices. You have the vertices. You just say that it is if it is a click or not. So I ask you, is it a click or not? So is finding always as easy as checking? Of course not. Finding is always more difficult. So we will see, we'll prove that P is in NP, but is the reverse also true? So this is obvious, but if someone can prove that NP is also inside P, then the person will receive a big prize, because then all problems will be solved. Either, yeah, all problem will be solved. Like you can decode any password in a short time. I don't know if that's the solution to the problem or a bigger problem. Okay. The proof that P is in NP. We said that you are in NP if you have a short certificate. Yeah. So You have, let's say, you have but we want to use that to show that P is in NP. So that short certificate is the key. So let language L be in P, and there exists a polynomial algorithm A for L. So a polynomial algorithm for producing members of L, or for example, when I asked you if 3 factorial is 6, you had to calculate 3 factorial and tell me if it is 6 or not. So you didn't check your certificate. You found the answer. You tested it. You didn't verify it. You didn't verify a solution. You produced the solution. So you produced the solution. And this is the production of the solution. So you have an algorithm. I ask you, is 3 factorial 6? We calculate 3 factorial. You see a 6. Yeah, yes, it is 6. Then you can define a verifier with a certificate that would act the same as this function, but with the certificate. For example, in completeness and complexity, you see these things that at the beginning they sound strange. You can say, calculate 3 factorial if it is 6, and if 1 plus 1 is 2, or if, like, I don't know, if you multiply the 6 and divide it by, multiply and divide it by 2, and you get 6, then it is accepted. So the second thing that you are checking is a useless, stupid thing that you can simply ignore it, but you have a certificate for it. You say, if 3 factorial is 6, and then 6 plus 2 minus 2 is 6, then it is accepted. Yeah. So you can have a useless certificate, because you can have a certificate that you can ignore it. You can even have a smart certificate. If you can define a certificate that would work together with your solution, then you are in NP. So you just define a useless certificate and put it beside a P problem, it becomes NP. And this is a story. Most computer scientists believe that P is not NP, meaning that there exist problems in P that have no polynomial time algorithms, but it has not been proven. So we don't know it. So if P is NP, then verifying cryptography breaks optimization. Sorry, this should be a dot here. Verifying cryptography breaks optimization becomes easy, and yeah, all difficult problems become easy. But there is something. How one can prove that P is NP. There was a problem. There is a problem, the prime problem. From the beginning of the history till 2002, everyone was sure that that's not a P problem, that's an NP problem. In 2002, 3 Indian scientists whose names start with A, K, and S, I have forgotten their names, proved that problem of primes is in P. So they proved that there was a problem in NP, but actually it is in P. Did it prove that P and NP are the same? No. they proved that just one problem has that characteristic. They proved that just one problem has that characteristic. You should have a way to prove that all problems which are in NP are in P. So what, by just moving one problem, you cannot. But there are problems which are called NP complete. NP complete. These problems are known to be at least as difficult as any NP problem, and is proven that they are themselves in NP. If you take just one of these problems and solve it in P, find a polynomial time solution for one of these problems, you have proven that all NP problems are in P. If you take just one of them. And this is the story that I'm going to tell you about NP completeness and the trial of proving that P and NP are the same, or to prove that a problem is NP complete and not looking for a solution for it. So if you have a problem, and now that because of the advancement of artificial intelligence, you get bigger and bigger problems. If someone, you are hired and someone gives you a problem, and you can prove that this problem is NP complete, then you tell your boss that this problem cannot be solved on a normal computer in an acceptable time. We need an optimization, an approximation solution for this. We cannot get to the exact solution. It takes too much time. We cannot give such a service to our clients in real time. It is impossible. So this has such applications. To reach that point, we need to know some basics. Polynomial time reduction. Reduction doesn't mean making a problem easier. It doesn't mean making a problem easier. Look at this. This is a point of confusion. And the ones who were not, who were distracted, please listen. A is reducible to B in polynomial time. You see, this sign means B is bigger. So why do we say A is reducible to B? If we have reduced it, why is this sign showing that B is bigger? Is it the mistake? No. This means that this problem is more difficult in the term of time complexity, more difficult, or at least as difficult as A. So you did not reduce the time complexity. You reduced the difficulty of the problem for a human. So a human now understands the problem easier. But if you want to solve it, so you can see the solution or the problem better based on your background. But this problem usually is more complex than this one. It is easier to understand for human, but is more complex than this one. So for example, you have an iterative function, which is big and complicated. As a human, you look at it, you don't understand what's going on. You write it in one line in a recursive form. Recursive is easy to understand for humans, is more difficult for the machine to solve. So this This is an example why we say reduction. A is reduced to B. It doesn't mean that the B is easier. B should be. So if you apply a reduction that makes this problem easier, this is rejected. This is not this is out of the game. No, reduction should make the problem more complex, or at least as complex as this one. But the complexity that we are talking is time complexity. So you have found the solution. So here, perhaps you didn't have a solution at all, or you had a solution, but it was difficult to understand. Here, you have a solution, but it takes more time. Yeah, this is about time complexity. So the time complexity of this problem is more than this, or perhaps they are the same, but this problem is easier to solve for the mathematician who is solving it. And the conversion of this to this should be done in polynomial time. So how does this work? You have any input, any problem in the in A, in language A, you convert it to another problem using a function, a polynomial function f, and then the problem is in B. You solve it here, or in our world of Turing machines, let's say, you approve that the solution exists. So you look at this and you say, you look at f of x, you say yes. If you said yes in a more complex space, there is also a yes in a less complex space. So the yes-no problem in this world is equivalent to the yes-no of this. So if you say a yes to x in this space, it should mean a yes to f of x in this space. And if you say a yes to f of x in this space, it should mean a yes to x in this space. But the key is that B is more complex than A, and we have created B in polynomial time. We read it like this. A reduces to B, A reduces to B, or B is at least as hard as A. Or if you can solve B, you can solve A. If you can solve B efficiently, you can also solve A efficiently. So F is helping you. So this is polynomial time reduction. So how does it work? So you given an input in problem A, compute f of x in polynomial time, then run algorithm for B here. On input f of x, return the answer. The answer is also valid for x in A. And I said there are problems that if you can prove they are in P, every problem will be in P. So we are going one step closer to that. Polynomial time reduction is transitive. It means that if A is reducible to B in polynomial time, then B is and B is reducible to C, then A is reducible to C. Yeah. And we use that. We use that in our story. This works like this. We have talked about it. This is a visualization of what we said now. A we convert to B. Input has been X, input becomes f of X, and then that they are equivalent. This is one very important example. The problem 3-sat. 3-sat is a kind of sat. I will talk about it. Is reducible to clique. It means the satisfiability of a 3CNF, a formula which is in conjunctive normal form. We have learned it in logics. It is like this conjunctive normal form. Where was it? I lost it. And let's also have an or. Mhm. So these variables can be anything. Yeah, these variables can be anything. And then the number of variables inside also can be anything. So we can have something like this. Conjunctive normal form. So we say the formula is CNF if inside the parentheses you have just or and outside you have just and. For example, this also is a CNF because inside we have just ors and outside if we had something we could put an enter. So this is a CNF, this is also a CNF. A 3CNF is a CNF in which these we call them clauses. The clauses have just 3 variables. This is a 3CNF, 3CNF, 3CNF. 3-sat is the satisfiability of 3CNF. So if you can say if a 3CNF like this is true or false based on the combination that you have. So given a 3CNF formula with k clauses, so here we have 3 clauses, 1, 2, 3. You can build a graph, 1 node per clause and literal. So for each clause, you should have a node for each literal. So you will have, so this is clause 1, clause 2, clause 3. You have 3 nodes for them. And also for each of these variables, you have a node. Yeah, you have a node for each of these variables. And we call them literals. You connect the nodes from different clauses that don't contradict. So if you have a G and G not here, you cannot connect them. And then this is not trivial in completeness and complexity. It takes like 1-2 lectures to explain this. but we prove that if phi is satisfiable, then the graph that we have made has a k-click. So if I make equivalent, if I make an equivalent graph of this, so I map this to a graph. I reduce this to a graph. I reduce this to a graph. I reduce this to a graph. That graph is not less complex than this. I would say it's more complex. It's, everything is in front of our eyes. And we prove that if this is satisfied and satisfaction of this is somehow represented in that graph, then if this is satisfied, then there is a 3-click in that graph. There's 3-click in that graph. So we have reduced the 3 set to 3-click. We reduced 3 set to 3-click. And because the click itself is a an NP, because we have a certificate, but we cannot solve it easily. And because 3 set is NP complete, then click also becomes NP complete. It means that if you solve click in polynomial time, then all problems in the world can be solved in polynomial time. So the next step is NP hard and NP complete. NP hard is easy. So you don't need to have a problem. The problem that you are talking about do not need it to be in NP. Just you should prove that, and you should prove that every problem which is in NP can be reduced to your problem. Let me read. A problem H is NP hard. Hard means difficult. Is NP hard if every problem in NP reduces to H in polynomial time. It means that every problem or every language, every problem in NP can be reduced to H in polynomial time. It means that you can turn every problem to H, and this problem H is at least as difficult as every problem in NP. So you can take any problem in NP and reduce it, change it, turn it, map it to H, to problem H. And H is more difficult than all of them or as difficult as them. Yeah. So this is called, we say that it is NP hard. Yeah, it is NP hard. But we don't know if H itself is in NP or not. We don't know that. If we don't know that, we can actually say that it is NP hard. This is easy. So, I mean, it's easy to understand. It is as difficult as any NP problem. It is NP hard. It is as hard as NP. It is as hard as NP. But we don't know if it is NP or not. We don't have a certificate for that. If we had a short certificate, then we would for sure say it is in NP. But we don't have a certificate for that. So because we don't have the certificate, we don't know if it is NP itself or not. But it is NP hard. It's as difficult as NP. But if we have also a certificate, yeah, we also have a certificate. It means that the problem is itself is NP and is also as difficult as any NP problem, or is more difficult than any NP problem. Then we say this is NP complete. It is NP complete. We know that it is in NP, and we know that there is no problem in NP which is more difficult than our problem. So if you consider any problem in NP, the problem that we have is not easier than it. We cannot do, you search the whole world for problems. The problem that we are talking about is not easier than that problem. And we have a certificate for our problem. This is NP complete, finished, complete. This this is very bad, very bad problem. Yeah, it's a very difficult problem. It is not easier than any problem. And the only solution, it's proven that the only fast way of solving it is through a certificate. This is a formal definition. And
Professor?
yes,
So I would know a problem is NP complete when it is proven that it's NP and also it's NP hard, right?
correct, correct, correct. It should be in NP and it should be NP hard. NP hard means that there is no, this is not easier than any problem in NP. There's any problem in NP is easier than this problem or as difficult as this problem. So you didn't find this an easier problem. You have a problem which is either more difficult than any problem or at least as difficult as the most difficult problem. And also you have a certificate for that. And because you have the certificate, it is in NP. So this is NP complete. Yes. Okay, there was a revolution in science around these years, 1971, 1973. Two people, Levin in Russia and Soviet Union, and Cook, I think he was American, almost at the same time, without being in contact with each other, they came to the same solution. So I think it's famous that the article that Levin has written is pure math. I don't know, it's two page, two page. It's a very short article, but these have changed the world. They have found the first ever NP complete. So they proved that SAT is not easier than any problem. It can be more difficult than any NP problem. There is no problem in NP which is more difficult than SAT. And they had also a certificate for SAT. So they proved that SAT is NP complete. It was the first NP complete problem that, listen to this sentence. This sentence is very important. We can reduce SAT to other problems to prove we reduce SAT to other problems. We don't reduce the other problems to SAT. We reduce SAT to other problems to prove that they are also NP complete. So you reduce 3 SAT to click. You don't reduce click to 3 SAT. 3 SAT is the source. You reduce it to other problems, which means that you make other bigger problems out of it. Even you say reduce it, yeah. Yes. So what is written here? SAT is NP, and every problem in NP, for every problem in NP, that problem can be reduced to SAT. So the problem can be reduced to SAT. It means SAT is the biggest one. And if you can reduce SAT to something else, that something else is at least as difficult as SAT. Yeah. You are reducing. So when you are proving, so the problem is that what are we, do you see it in your phone? Oh, okay. When we are proving that SAT is NP complete, SAT is bad. We are proving that SAT is bad. Yes. you reduce all problems to SAT. When you say reducing to SAT, it doesn't mean that SAT is better. The word reducing is meant because the problem is easier for human to understand, or somehow the mathematicians have decided to call it reduction, but reduction actually means making it more difficult. Yes, so we can take all NP problems in the world and reduce them to SAT. It means the SAT is worse than all of them, or at least if there is a problem which is very bad, is as bad as SAT, is not worse than SAT. So now I translate the word bad to complex. Say every problem in NP, and it means that all complex problems that have a certificate, all of them, can be somehow converted to SAT without reducing the complexity. All problems which have a certificate can be somehow converted to SAT without reducing the complexity. It means that SAT is at least as complex as every problem which has a certificate. Yeah. Then SAT itself has a certificate. So the fact that every problem can be reduced to SAT tells us, and the fact that SAT is NP itself says that SAT is NP complete. This was the first time in the history in 70s, it was at the beginning of the 70s, it was proven. Now, if you get a problem and you reduce SAT to that problem, and that problem itself has a certificate, it means it is in NP, even if it is, yeah, then you reduce SAT to that, then that problem is as difficult as SAT, or it can be even more difficult. That problem is also NP complete. It's a completely bad problem. This is the word reduction here is misleading. When you hear, I'm reducing it, no, this is just a word. Just by reducing it, make it more. It's like that. You make something by size smaller, but complexity more complex. So, for example, what is here? A certificate, a satisfying assignment for SAT, of course. A verified is you substitute values and evaluate the clause. You have a Boolean formula. I have claimed that true, false, true is the solution. You just put the true, false, true inside it, and then yeah, is it true or not? So this is the certificate for this. And how do verify NP problems? This is the part of that proof. I believe we don't need this in this course. I think that I have made you tired enough. Let's see what
Professor?
Yes.
So when you mention reducing it, it's basically like changing the language to my problem's language, just to prove that mine is NP complete or NP hard.
That is a good analogy. Let's say let's say you are native in Chinese, for example. I have a problem, I tell it in English, then someone translated it to Chinese. The problem didn't become easier, it's just more understandable for you. Yeah, that's a good analogy. Your language of problems. Yes, that's a very good analogy. Yeah. Then yes, we talked about this. The next one. This is the way you prove NP completeness. You show that a problem has a polynomial time verifier or certification. Yeah. So you can give it a certificate. Then you choose an NP complete problem like SAT, 3SAT, click, vertex cover, or ham path. These are the problems which are proven to be NP hard. I'm sorry, NP complete. Then you reduce one of these to your problem. One of these to your problem. You don't reduce your problem to something. And the direction is important. Yeah. If you reduce your problem to 3SAT, you have proven that your problem is easier than 3SAT. So you don't get anywhere. So yeah, 2 plus 2 is 4 is also easier than 3SAT. So what is it telling us? No. Yes, one reduction is enough. So you just take ham path and reduce it to your problem, because ham path comes from reducing vertex cover, and vertex cover comes from reducing the click, and click comes from reducing the 3SAT, and 3SAT comes from reducing SAT. Then it is indirectly proven, it's transitive, that SAT can be reduced to your problem. So this story started from SAT. Then SAT was reduced to 3SAT. Someone else proved that 3SAT can be reduced to click. This is a beautiful solution that we can understand. So for understanding this is a beautiful graph. One of the videos of Professor Michael Sipser, the video that I shared with you, one of his videos is about this, and it is a bit difficult, so you should watch the video several times. Some things are so, because he is a mathematician, and he's talking to perhaps to mathematicians, he jumps over things, but there are easier videos about the same thing, or you can ask me to explain that to you. It's a beautiful visual thing that you don't really need to be a mathematician to understand. This from 3SAT to click. Yes, so this is the way that we go. This is the zoom. So there are like a cleave, vertex cover. So I think I have not put this updated version on the website. I will do it. So you can also read about them. Yeah, you can read about them. There's a short explanation. This is also what you can have in mind, because in the future, when you are referring to a problem, which is you want to say, no, I'm not going to solve this problem, this is NP complete or whatever, then it's good to know some names. Yeah. Then this is a philosophical question. We don't go deep to it. It's a sad story of mathematicians. So we have the class P and class NP complete. So P is NP, but NP complete. Is there anything between them? So something, a family of problems which are not in P, but they are not also in NP complete. The answer is we don't know. So we don't know if there is another family of problems which are not in P, and also they are not NP complete. We don't know. Then this was also the problem that we talked about. In 2002, AKS, I forgot the names, these three Indian scientists proved that primes had been in NP. We didn't know if it is inside or not. They said, hey, it is inside. But nothing changed, because primes is not an NP complete problem. So if you can bring an NP complete problem from NP to P, then you get rich or you get kidnapped. Yeah. Yes, what would prove that you talked about it? Aha. There are ways to solve these NP hard problems, the problems which are very complex. NP hard problems, it means that they are difficult, they're very difficult, but not necessarily we have a certificate for them. That's is not it doesn't matter. There are different ways to solve them. If you study algorithms too, you will learn these approximation algorithms. That's a little bit of it. And special cases we have seen in our lives. So there are different ways. Approximation, fixed parameter tractability, and heuristic. Heuristic, if you study artificial intelligence, you learn about heuristics. Heuristics is a kind of logics that, let's say, logic of approximation, something like that. I mean, no one in the world has said logic of approximation, but we are not mathematicians. We can say things that perhaps they are not correct. And so what is approximation algorithms? I say that we have, like, for example, two approximation. I tell you from here to Dubai Mall is 13 minutes. If you could directly walk to there, and for sure, no one on the earth can reach Dubai Mall in less than 13 minutes if he or she walks to there. If it does, I mean, not a speed runner, no. I mean, normal human cannot reach it. Because if there was a direct way, it would take 13 minutes. There is no direct way. So for sure, we know that nothing better than 13 minutes is possible. So if someone says that, hey, actually, we have found the shortest way, it is 26 minutes. Shortest way that we could find. It's not proven. It's not proven to be the shortest, but I say, okay, it's a two approximation of the bottom line, two approximation of lower bound. So you have a lower bound, which is not necessarily possible. You use that to say how good your approximation is. And this kind of approximation is very, very important. There are problems that if you want to solve them, they will take with a good computer, it will take like 200 years to solve a problem. And you say, hey, okay, give a discount, just take it easy. I give you something acceptable in like 3 seconds, 20 minutes. So instead of waiting for 200 years for an optimal solution, you take something that is like 5 times worse than the bottom line, but in 3 seconds. So this is the philosophy of approximation. So we have two approximation, 1.5 approximation, and so on. This we have. This is yeah, out of the scope. This you will learn in artificial intelligence if you have not learned it. And special cases, you just take a problem. For example, mathematicians do these things that you have a problem which in general is not solvable, is not, so you don't know the solution. And the problem is a non-linear problem. You turn it to a linear problem, you solve it. This gives you an idea, and you use this idea to solve the bigger problem. Or you solve the problem in a special case, then you use induction to expand it to a bigger solution. Yeah, these are the special cases. Yeah, I think we are done. This is just an summary. So P problem solver in polynomial time by deterministic Turing machine. They are tractable. NP problem whose yes instances have polynomial verifiable certificates. And polynomial reduction is a polynomial time function mapping A instances to B instances, preserving yes and no. So if you would say yes to a solution and a problem in A, if you convert them to B. So I ask you in English, is 3 factorial 6 or not? You don't understand. Someone translated to Chinese, you understand, and then you say in Chinese, you say yes. Then this yes is as valid as yes saying yes in English. It doesn't matter. But for you, as a Chinese speaker, that is easier to understand, but the complexity of problem is not reduced. That was a good analogy. This is your language of problems. It is reduced to your language of problems. But the calculations that you did in your head, number of steps that you took in your head, is not less than the number of steps I would take in my head to say yes or no. NP hard is every NP problem can reduce to H. It means that H is at least as difficult as every problem in NP. NP complete is when you have a problem which is NP hard and is NP at the same time. Cook-Levin, the revolutionary articles they wrote that SAT is NP complete, the first proven NP complete problem, foundation of the whole field, and any NP complete problem is in P, is not. If we say that, if we prove that, then these two will be the same. Also, we have not proven that the AP and NP are different. They have not different. And we got to talk about the example of primes, that the fact that this problem was in NP and then we brought it to P doesn't mean that P and NP are equal.